Hi, and welcome back to Cloudlets AI, where networks meet cloud. And today we're going to talk about AI and specifically about AI Network Fabric and the different ways to implement it. And we have our AI Network Fabric expert, Yossi. Hi, Yossi.
Hey everyone,
Thank you for joining us.
thank you for having me.
We have an issue with AI Network Fabric, right? We have some requirements. We have some specific things we need to know about. Let's understand first, what is the problem? What problem are we trying to resolve?
Great question. Essentially, AI networks rely on two fundamentals. First one, they use RDMA, Remote Direct Memory Access. Now, the reason AI networks use RDMA is because we want to reduce latency of read-write operations as much as we can, right? Now, the second thing we have, or the second characteristics we have in RDMA or AI networks is elephant flows. These folks, the GPUs that participate in a cluster, usually send very long flows of data. Now, these two characteristics that I mentioned, the RDMA nature of it and the elephant flows, causes several problems. You want to talk about it?
Oh yeah, please.
Okay, so essentially RDMA is not tolerant for loss. RDMA works with an algorithm called go back N. So what happens is we lose a lot of time, and time is expensive when you're talking about AI networks.
Because job completion time means the utilization of the GPUs, and this is very expensive.
Exactly. So first thing first, you're not allowed to lose any packet when you're talking about AI networking or RDMA networking in specific. Second thing I was mentioning is elephant flows. Now, the problem with elephant flows is that they naturally have low entropy, right?
Which means you cannot efficiently load balance, which means you will have packet loss, which contradicts the first.
Exactly. So essentially what happens is with the classic or standard ECMP or hashing mechanism that you have today, what happens is you bombard some specific links in your network while other links or other resources of the network are essentially idle.
Okay. So we understand the problem, we understand what we need to do, and basically there are two main philosophies about how to resolve this problem. One is based on the endpoints and things we do there in order to mitigate congestion and to ensure all the things you mentioned. The other is based on a fabric, the network itself. So let's talk about both of them. Let's start from the endpoints. What do we do there?
Yeah, so you mentioned perfectly. You have two types of approaches. The first type, which is endpoint congestion control or endpoint scheduling mechanisms, are talking about how to solve the problem once it occurs, okay? Then you have a type of solution that is talking about how to proactively prevent the problem from happening. Let's deep dive into the NIC-based or the endpoint-based solution. So if you look at the industry today, you'll see all types of vendors. You'll see NVIDIA offering their Spectrumx. You'll see all sorts of collaborations between switch vendors and NIC vendors trying to somehow integrate the NIC into the switch in order to solve it. But there are a few fundamental problems with it, right? First one, it's very costly, right? It's costly because the super NIC or the DPU costs a lot of money, right? That's first. Second, it's costly because the DPU usually consumes a lot of power and a lot of cooling that it needs. And that's basically the worst solution you can choose. And I'm being specific here when you're talking about TCO, okay? Now, it solves the problem of elephant flows because then you can activate on your network some kind of smarter load balancing mechanism, like
some kind of packet
spraying and stuff like that, and then somehow reorder it on the NIC side, right? So it does solve the problem, but then it introduces another problem that we haven't mentioned, and this is an operational problem. Now, the operational problem that I'm referring to is specifically with fine-tuning the network. If you want to have a good congestion control mechanism or a good reordering mechanism in your endpoints, you need skill set. You need people to maintain that, right? You need people to go ahead and prepare your infrastructure every time you want to run a model. So it solves the problem on the technical side. It's costly and it requires some decent expertise and decent skill set.
Okay, so this is a valid solution, but it has its flaws. What about resolving it or avoiding the problem altogether in the network, in the fabric itself?
So, if you ask me, when I'm thinking about AI networks, I think the optimal solution would be chassis, right?
Yeah.
Imagine just taking a bunch of GPUs and connecting it into one chassis, right? And then the chassis does all the magic.
Yeah, it's a single hop Ethernet. The backplane is
exactly. It's a single hop from NIF to NIF, or from port to port, right? From Ethernet port to Ethernet port. It has no congestion in it, right? The connection from the NIF to the fabric and then to the NIF is pretty much end-to-end scheduling, and you lose no packets. And in terms of operations, in terms of how to maintain that, it's
plug and play, right?
It's given. Every guy with a CCNA can do it.
But if I have 10,000 GPUs, there is no such chassis.
Exactly. Now that's the major problem. And we have a solution for that. You want to hear about it?
Oh yeah.
Okay.
Never heard about it.
Essentially what we did with DriveNets is we took a chassis, we distributed it, we disaggregated it, but that's a whole different topic. So we disaggregated it, we distributed it, and essentially we made it scalable to an extent the industry have never seen before, right? So essentially our solution is based on two building blocks. We have the NCP and NCF. While NCPs are equivalent to the old-fashioned line cards, and the NCF is equivalent to the fabric board that we're used to from the backplane of the chassis. And essentially this distribution of the chassis gives us the benefits of a chassis, which is end-to-end VOQ system, fully scheduled, lossless by nature, right? And then scalable, okay? So in fact, you can have a chassis-like solution, which is optimal in terms of operations and in terms of technical abilities in AI networks, and you can have it scale up to 32,000 GPUs in a single cluster.
Okay, this is very cool. So thank you, Yossi. This was mind-blowing. The three things we need to remember about resolving the AI fabric or AI networking problem with large clusters of GPUs, usually used for training, is one, the problem itself derived from the fact that we use RDMA, which means that we need a lossless, scheduled, high-performance fabric, and the ebb and flow nature of the information distribution within the cluster, which means classic load balancing like ECMP would not work. So we have two solutions. This is the second and third point. The first solution is endpoint scheduling, which relies on the endpoints, which needs to be very smart, very compute and power savvy, like DPUs. This is a congestion control or congestion mitigation solution, which brings you so far in terms of performance, but it costs you a lot and also is very complicated to manage. This is coming from vendors like NVIDIA with their Spectrum-X, and also other vendors that are cooperating in the Ultra Ethernet Consortium, for instance. And the third point is the network-based solution for resolving this issue. The network-based solution is practically building a chassis which is distributed, hence disaggregated distributed chassis, which means you have no packet loss, a lossless and fully scheduled fabric, but without the scale limitation of a chassis. And this is coming, of course, from DriveNets with our DDC, but also from other vendors. We will talk about Arista DES in the next movie. So this is what you need to remember. Thank you very much, Yossi.
Thank you for having me.
And thank you for watching. See you next time on CloudNets.